morning, everyone. I'm going to go ahead and start recording. Now, it is October 30th, which is the day before Halloween. That's why the background looks like it does. I love Halloween, not as much as my wife. She likes it even more, but I'm kind of Christmas nut. She's kind of a Halloween nut. But one of the things that I really miss is that if we were together, I would be doing all sorts of demos for you this week because, hey, it's Halloween and I love doing demos, and demos are fun. So I don't want to miss that. So what we're going to do is we're going to go, is this working? This is working. All right, so we are going to go just on a little trip here. That's my backyard, and I happen to have set up a couple demos because I can't resist. Right.
Could you speak up, Doug?
Okay. That's not what I meant. Okay. I sure hope you can hear me. Let me check the volume.
Speak up a bit.
I will try.
All right.
Okay. Is that a little bit better? I hope so. I don't know if you can hear me. We're going to, you know what? I bet you if I do, I decided to do this morning. So, this is not something that I had pre-planned. All right. Can you hear me at all when I do that?
Yeah, we can hear
Okay, good.
pretty well.
All right, so yeah, so I'm just gonna do two quick demos for you here, but gotta be safe. You know, safety is important. Okay, so I got my safety glasses on. Got a black coat. Now, this first reaction I want to do for you is one that we actually did in Chem 202. This is the foam reaction, but we're going to do it a little differently today. We're going to bring in Bob. So Bob is our pumpkin, and Bob loves to eat Halloween candy. The problem is Bob likes to eat a little too much Halloween candy. So we're going to see what we can do with Bob. And we're going to put in a little bit of the concentrated hydrogen peroxide. So this is our 30% hydrogen peroxide. Okay. Just put a little bit in there. And if you remember, we did this, as I said, in Chem 202, talking about kinetics, right? Speeding up reactions. Because hydrogen peroxide will decompose on its own, but it takes a long time. So we're going to try to capture the bubbles here. Now I have everybody's best screwdriver, because, like I said, I don't know. And that's one thing I forgot to bring from work. Whoops. Okay, so let's go ahead and take this now. Now I've got a saturated solution of potassium iodide. So let's see what happens if we feed Bob too much Halloween candy. Okay? Oh, here we go. And here's Bob. Oh no! Ah! That's a problem. This is what happens if you eat too much Halloween candy. I try to tell my kids this, but they never listen to me. So there's, oh wow, that one was quick this morning. Okay. Just something for fun. Okay. Now, whoa, there we go. All right, so let me move Bob out of the way. I had Bob set up on this really old thing you may have never seen anywhere. They're called CDs. All right, one more for you quick, which is another actually one from the kinetics lab, because I just love the kinetics lab. And that is lycopodium powder. And so I have this in our plant spores. I'll be filling my yard with it too. Well, the trees will be filling my yard with it too. And what we're going to do is we're just going to send these through a funnel. We're going to see what happens if we do that. Now, this one I'm really not sure if you're going to be able to see or not. There is a flame going there, but there's so much of this sunshine. Wow. I'm a chemist. I don't go outside. I don't know what is this sunshine stuff that we have here. All right, so let's see if we can do this. Make sure my flammable starting material is put away. All right, here we go. In 3, 2, 1. Oh, it worked. All right, so nice fireball there. Okay, right, because something that doesn't normally react very quickly because they can't mix the oxygen and the lycopodium. But when you put it through a funnel, then you get good mixing. And now all of a sudden you get a good reaction there. Okay. Random way to start, but I just can't resist doing a few demos. So let's come on back inside here. Okay. And switch back over. Okay. Let me turn this down. All righty. I'm getting an echo. Let me turn this down. Okay. All right. Breathe. It's fun. Smells like burnt like a podium now. All right. Are you guys hearing me okay? Because I'm doing this a little different. Okay, thank you. I'm doing this different this time because I want to try to do this a little more interactive with our our lecture today. So, in fact, let me. There's lycopodium powder on my iPad. Come on, Zoom. No, I am muted there. Okay. So, all right, I hope you're not getting an echo, and I hope you can all still hear me. So let's talk about Diels-Alder reactions. So this is our second in our Nobel Prize winning reactions, right? We looked at the Suzuki coupling last week. Now you've already looked at Diels-Alder reactions in class. So some of this is hopefully going to be review for you. And then I'm going to try to throw in some new things for you to extend what you've seen in class and kind of help you out a little bit. But oh wait, my kids had to sneak in there. I haven't been putting up enough pictures of my kids. So this is a couple years ago for them each. It's their first Halloween each. Okay. All right, so let's go into Diels-Alder. Okay, so we've got our reactions, and hopefully when you're looking at this, you're thinking, oh, look at that. I see a diene, I see a dienophile. Chances are good we can do a reaction here. And if we think about the curved arrows, right, we can do it. And this is something that, as I'm saying, should be fairly straightforward for you at this point. We can draw, right, we have this 6-electron process, this concerted pericyclic reaction that occurs. And we can do it a couple different ways. When you draw these arrows, you can either draw them to the bonds that will form, right? You're going to form a new bond here, you're going to form a new bond here. Or you can draw them to the atoms where the bonds will form. And I talked with Dr. Weinschenk and Dr. Heemstra to check, and they were okay with either one of those. Dr. Weinschenk and I both tend to go towards where the bond is forming, but either is considered acceptable for that. So what I want you to look at first, though, is to remind yourself, looking at the stereochemistry of the dienophile, right? That's the double bond here. Okay, and so if, that was an ugly way to highlight that. All right, if we look at this, right, we started out cis, and then when we're done, both those cyanides are on the same side of the molecule. They're still cis. Likewise here, we started with trans, we ended up with trans, because if you think about it, in Diels-Alder, you're really just taking the two pieces and you're just gluing them together. There's no carbocations, so for rearrangements or anything like that. And so what we can say is for the dienophile, that the stereochemistry is conserved. So if you started cis, trans, EZ, however you started with that dienophile, the final product will still have that same stereochemistry, okay? So in the experiment itself, you're going to look a little bit about the stereochemistry of the diene, okay, to remind you of that, because I know you've talked about it, but I just wanted to kind of get reminded because it's been a couple weeks, although I think that's probably on your next test for Diels-Alder. So was that November 9th, I think? So this is good review. I'm just trying to help you out with that. All right, so that's some of the stereochemistry. Now let's look at the regiochemistry. And so when I look at this reaction here, I see my diene and my dienophile, and I've got a pretty bulky group up here. I've got some bulk down here. So I'm just going to try to make a prediction. I'm going to say, you know what? If I just think about sterics, then I'm going to guess that we're going to do something like this, okay? So then we can do our reaction. And so I'm going to predict as my product. Okay, I'm going to get what? I get double bond there, then this would go oxygen, and then this would be double bond oxygen and a hydrogen, okay? So looking at the bulk of this group at the top and this thing at the bottom, that's my prediction. All right, so let's go ahead and look at that. And whoops, that's not what happens. In fact, not only is it, is that not the major product, we don't actually get any of it. 100%, this is the only Diels Alder product. That is not what I predicted. So what does that tell me? Well, that tells me that I can't actually use the stereochemistry or the sterics to predict regiochemistry. In fact, here's another example of one where we look at it and we have a strong preference for one of the products over another. So if we're trying to figure out how to look at the regiochemistry, we actually need to look at the high energy resonance structures. Remember, in organic chemistry, if you don't know what the answer is, it's always resonance. So if you're not sure, just answer that. You got it, like most of the time. And it is in this case too. So let's look at a couple of these resonance structures. Let me zoom in here and draw another resonance for you here. We've got a double bond, so we got a lone pair here. So I'm going to bring this lone pair here. I'm going to move this here, and then I can move that up onto there. And then I'm going to move this double bond here, and we can do this because we have all of these oxygens. All right. So what that gets me is, what do I have? I've got dun, 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 dun. Then I've got my oxygen here. Get that off there. Now I have a double bond here, a double bond here. And importantly, I have a lone pair of electrons and a minus charge. Now, if you think about that, in the normal circumstances, we just made a primary carbanion, right? That's not very good. Like I said a moment ago, these are the high energy resonance structures. So they don't exist a lot, but it turns out that they do exist enough to influence the chemistry. And one of the reasons why I always kind of like this is that we talk all the time about, major and minor resonance structures and things like that. And it's important to realize that the minor resonance structures are still there. They may not be as important, they may not be the most stable, but they're still there and they can still influence the chemistry. Because if you think about it, I'm missing a charge here. I've got to have a plus charge up here. Okay, if you think about it, I've got now a minus charge and a plus charge near each other and a minus charge and a plus charge near each other. So that charge separation is going to line the molecule up so that we would get this product here. All right, let's do that with this one down here. What if we did our high energy resonance structures? Well, let's bring this down here and that over there. Okay, and then I'm actually going to bring this double bond down here and this one over up onto that carbon. All right, so dun, 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 oxygen out to there. I've got my double bond here and a double bond here. Once again, I'm making that primary carbanion, which if you think about it, when we first started in organic chemistry, we would have said, no, no, never do that. But yep, you can. It's minor, but it is important because, whoa, come back. We've got a plus charge here. Sorry, writing on the iPad is never the neatest handwriting in the world. And goodness knows, my handwriting was not neat to start with. Okay, but once again, we can have this interaction with this positive and this negative, and that's what's going to line it up. Now, we don't get quite as good of an interaction here, right? Because the positive on the oxygen doesn't help. Up here, the positive on the oxygen and the minus on the oxygen helped. Here they don't, so we do still get some of the minor product, but we definitely can see that if we were to line up this negative charge and this positive charge, then that lines the molecule up the way that gives us our major isomer. Okay, and so, oh, I already did that for you. So what are we saying here is that we're saying, oh, we're going to try this. We're going to see if this works. Siri is not a very good chemist. If your diene and your dienophile are both asymmetric, then the major isomeric product is the one that exhibits the most favorable electrostatic attraction of bonds undergoing bond formation. Oh, Siri, what did you do to us? I am if you're dying and you're done. It did it better this morning when I practiced. All right. If the diene and dienophile, cyanophile, I don't know what that is. Okay, this may not be worth it. I thought it was going to be so much faster than my writing because I tried so slow. I will make sure I have this fixed in post. I love post. Post is great. But so if the diene and the dienophile are both asymmetric, then the major isomeric product's the one that exhibits the most favorable electrostatic attraction of the bonds. So, and that's from those high energy resonance structures. Okay. So let's look at some actual reactions here. And as always, if you have questions, please put them in the chat or just holler. I'm happy to help with them. Okay. So let's look here. And what we've got is we've got cyclopentadiene. That's this molecule right here. And then we're either reacting it with maleic acid or fumaric acid. And if you notice the relationship between the two of these, right? Maleic acid is the cis version and fumaric acid is the trans version. I'm pretty sure you saw this one in class or something similar. And so we can look at all the possible products, and this is kind of what leads us to the data that helps us know about the endo rule. I'm not going to get that far into this yet. What I want to do is I want to talk about the NMR a little bit, because that's what we're doing in class. How do we have, what evidence do we have to support which products we made, and how do we know that? So I'm going to focus, we have two options in this first reaction, and I want to start with this first one here. And let's look at this one where my CO2H's go down. And let's bring up the NMR of this reaction, okay? Ooh, that's a lot of lines. Okay, so what's going on? Because there's something new that happens here that I want to talk about. So let's look at our molecule again. Okay, and we have our double bond. And then we have our CO2H and our CO2H. Now, again, if you are assigning the NMR, the proton NMR, you want to draw out your protons. So I also have two protons that are out here on the double bond. I've got two protons that are up here on the bridge. I've got two protons that are on the bridge head. And then I've also got two protons sticking out here above your CO2H's. Okay, that's a lot of protons. That's why we get a lot of signals here. All right, so let's look and see if we can try to identify it based on what we know about NMR. All right, so I'm actually going to start with my green protons because, actually, no, I don't. I want to start with my red protons. Let's start with the red protons because they're here on this CO2H, right? They're on this carboxylic acid. So they're OHs, so we may or may not see them. We do in this case, but if we do, they're going to be broad. Their integration is going to be funny. And if you go back to your correlation tables, carboxylic acids appear around 12. There we go. So that's going to be our hydrogens that are due to that. All right. So then we can look at our integrations and we can see that we have around 6 to 6 to 6 to 3 to 3. All right. That probably reduces to 2 to 2 to 2 to 1 to 1, which is a little bizarre because all of my other protons come in pairs. So we'll have to try to figure that out. But now let's look at the green protons. They're on a double bond. That means they're going to be shifted downfield. So these two protons are going to be these ones here. Okay. Now remember that the instrument that we use, well, actually the software we use, marks the solvent. So it marked the DMSO. It also marked this HDO. That's water. And now we didn't use water as a solvent, but what does that tell us? It tells us that our sample was just a little bit wet. Now, sometimes when you got all these peaks, it's hard to tell which one. If you look, there's actually a little red mark above these. Those are the ones that the instrument is marked as solvent. So you can, it's easier to see it because from the top down, it gets a little hard to make the connection sometimes. So if it's got a red tick above it, the instrument thinks that it is solvent. It's usually right. Not always, but it's usually. Okay, so then we have the purple and the blue hydrogens. And if I think about the blue hydrogens are one bond away from my double bond, right? So there's a double bond here near it, okay? So that's gonna probably cause me a shift. And then my purple hydrogens are right next to a carboxylic acid. So they're also gonna be shifted. So they're probably these two right here in the middle. And so what I'm gonna have to do is I'm gonna have to use my tools. I'm gonna have to use my chemdraw, I'm gonna have to use my Spartan, at the level that we're at right now to try to identify these. And it turns out that the purple hydrogens, why am I circling in blue? The purple hydrogens are the ones that are more upfield. and the blue hydrogens are the ones that are more downfield. Again, at the level we're at, that's not a prediction that I would expect you to be able to make. That they're in that region, yes, but not which one's which. So then we're left with our yellow hydrogens. And they're not near any other electron dense groups or anything like that. So I would expect them more upfield, more around 1. But something kind of weird happened, which is that I'd expect them to be here, but I've got 2 peaks in there. So this is these 2 hydrogens here. Let's zoom in. Let's look at this and make sure that we're not just seeing an artifact. And yes, we actually do get 2 peaks down here. So what happened? This is the first time that we have seen this, but we're going to come back to it a little bit later on today, which is that we've been talking about chemically equivalent groups based on their nearest neighbors. But it turns out that the 3-dimensional region in space also matters. Because if you look at these 2 hydrogens, one of them is sitting above a double bond and one of them is not. I mean, it's right above that double bond. And that double bond, you've got these pi electrons in here that are being shared here. So this hydrogen is just sitting right on top of this mass amount of electrons on the one side, and the other side it isn't. So they're not in chemically equivalent environments. And as a result, they're going to appear differently. Now, where exactly they appear, which one's which, is sometimes a little hard to predict. We would usually say you've got more electron density around it, so we should be more upfield. And that is often the case. However, in this case, it's a little bit backwards. Hint, hint for the post-lab or the experiment. There's a question about this. See, you listen to the pre-lab or you come, you get free questions. So in this case, HB is the one that's more downfield. HA is the one that's more upfield. I actually would not try to make that prediction without other techniques. And we do have other techniques. We haven't even talked about 2-dimensional NMR and COSIs and NOSIs and NOEs and all sorts. I mean, we love acronyms. There's all sorts of other techniques that we can use to figure out which proton is which. For us, I used Spartan.
So the one.
Okay. All right, so we can assign that one. Let's look at the other product. Okay. Let's look at this one here, or the other reaction. Let's look at fumeric acid. And we don't have as much symmetry in this case. So the one above the alkene is more downfield in this case, yes. Question that came through in the chat. All right, so let's look at this molecule here. So we're going to try to assign this. Now this gets a little bit messy here, so I'm going to do it a little bit differently. I draw in all of my hydrogens. Okay, so what I'm going to do is I'm going to say that this is HA, this is A. Actually, let me make the labels a different color so they're a little more obvious. HA, HB. You can number them or do them however you want. HC, HD. What did I do with my HEs? Where did HE go? That's interesting. I seem to have forgotten the letter E. Oh, well. HF. I'll come back to that. Now, in this case, I'm going to go ahead and give this away, that these 2 protons on the left are separate again, because I've got an extra peak in here. So what happened? So not only are these 2 up here, which are referred to as geminal hydrogens, because they're Geminis, they're the twins, they're on the same carbon here. They're unequivalent. In this molecule, these 2 hydrogens end up being unequivalent. So we're trying to say, how does this 3-dimensional arrangement cause that? What's going on here to get us all of these differences? Okay, and so you can kind of walk your way through this. We have a couple things. I do happen to know, based on another reaction, that this was an impurity. Okay, this is actually student data from last year that we have. Okay, so similar to what we did a minute ago, I'm going to say this is HA and this is HB. Okay.
Then HC and HD, these are the two hydrogens. Oh, they're now not equivalent either. The ones next to the carboxylic acids, because one of them is pointing endo and one is exo, right? One is axial and one is equatorial. So those are different chemical environments. Now, these two, again, would be very hard to figure out which one's which. I used Spartan. This does match the literature. If we have HD and HC here, so I used Spartan. Okay, I love Spartan. This big peak right here, notice it has the red at the top of it. So this is our DMSO, so that's solvent. That's why I don't have to assign it. Then this one here is HF. Those are the bridgehead ones. But what I really wanted you, or part of what I wanted you to notice as well, is that once again, I now split this into two peaks, and these are the ones that were attached to the double bond. So why is it that in this molecule, where you have one carboxylic acid up and one carboxylic acid down, that affects the protons on the entire other side of the molecule, right? I'm talking about these groups over here affecting these over here. They're like way away from each other. Or are they? Dun, dun, dun. Sorry, sound effects too. Let's look at the molecule. All right, here's a place where looking at our interaction can be important. I'm talking about these two protons here. And I'm talking about the carboxylic acids on the other side. And if you look at this, you've got one of these that's kind of close to an oxygen. And then this hydrogen back here isn't really near the carboxylic acid that would be equivalent for it. Again, when we use this model, we can get ourselves into trouble because we haven't filled in the space. We haven't shown you how large these atoms actually are. So let's switch to space filling. Whoa, it's huge, but look at this. This proton and this hydrogen, or the proton and the oxygen, are like right next to each other. So they really do interact. All of the electron density on this oxygen affects that proton, whereas on the backside, you don't have one that's next door to it. Now, it is really close to this one as well, but that actually also happens on the back. So your bridgehead one's end equivalent. The take-home message I want you to get here is that NMR has more information. The three-dimensional arrangement can also affect the number of signals that you see. You can get splitting because of through space interactions, not just through bond interactions. Okay, that's kind of my big thing there. And these are all Diels Alder adducts. Okay. Oh, hey, more kids. I just can't. It's just one of those things as a dad, especially that picture on the left. I'm sorry. That's just and I guess I was wearing the matching lab coat. Yes, I have matching lab coats with my kids. Thank you to my mom. Okay. Now, coupling constants is something that I told you we were going to talk about when I introduced NMR, and now it's time. So coupling constant is how much splitting there is between the peaks. So remember, the nearest neighbor splits you into a multiplet. The coupling constant is how much splitting there is in that multiplet. So notice that the lines here are closer together than the lines here. That's what I'm talking about. I'm talking about the distance between the lines here. Up until this point, we haven't really worried about it, but it turns out it has a lot of information. And that's referred to as the coupling constant, and it's given the abbreviation J because, okay, it just makes no sense. I don't know why they use J. There's not a J in that word, but although we have too many variables that are C, so there you go. All right. So what we're talking about is the how much of an interaction, how much of a splitting is the nearest neighbor doing? And that is influenced by a lot of things. And this red paragraph at the end is really important here. The magnitude of the coupling constant can give us a lot of information. It can tell us what it's bonded to, what type of an atom, proton versus nitrogen versus carbon versus fluorine. It can tell us the angle, actually. That's kind of odd, but based on the dihedral angle influences the coupling constant. It can tell you if there's hydrogen bonding, how many bonds are in between. So the coupling constant can actually give you a lot of information. And we're not going to delve too deep into it. If you want to take an advanced organic course or spectroscopy course, you can spend a little more time in there because it is interesting. But there are a few things I do want to try to explain why we've been seeing some of the NMRs we've been seeing. So why is it that sometimes things appear as a doublet or like a quartet or a doublet of doublets or something different? Why do we see something a little different? Okay. You know, I don't know if I really want to spend a lot of time on this slide, but the main thing is this kind of shows you how this works. The spin state is sensed through the bonds, because if your electron has a spin, then that affects the nucleus that it's next to, right? That's the whole principle with NMR. But if you're sharing electrons between two nuclei, then the spin over here should affect the electrons in between, which then affects the spin over there. Okay, so the electrons in the bond are influenced by the relative spins of the nuclei on either side of them, or of the two nuclei that they share that with. And that's how we get this coupling. That's how we get this interaction here. All right, so a couple of points about it. When we talk about coupling constants, they're reported in Hertz. And one of the things that I always found very, very interesting is that it's a constant. It doesn't matter what your strength of your magnetic field is. It doesn't matter the strength of the NMR. The coupling constant stays constant from one NMR to the other. Well, that's kind of nice. And so it's independent of magnetic field strength. Now, the type of bonding that we've been talking about up till now has been this one here. Today, I introduced you to Geminal, which we'll show you in a second, which is when they're on the same. But 4 and 5 bond. Now, initially we said it was only your one nearest neighbor from one carbon away. So if I'm looking at this proton here, all right, so then the next carbon, I'd look at that proton there. Our instruments that we use here at Emory are powerful enough, and one of the NMRs that your samples will run on is our $1 million instrument. It actually did, well, I'm cheating a little bit when I say that, and I may have told you this or not, but the grant was $999,956. So it's about, you could only ask for $1 billion, so we got as close as you could. We're $44 off, but Emory had to pay a little bit too. But anyway, so our instruments are powerful enough that we're seeing the 4 bond and 5 bond coupling and things like that. So when you're working on the Suzuki, because I know that you've all already worked on that and you've thought about it, and you're not waiting until Sunday night to do it, since it's due on Monday. But if you've been looking at your NMRs, you'll notice that there's a lot of fine structure, right? We have the main peak, and then sometimes there are shoulders or little tiny peaks. That's this other type of stuff that's going on, the 4 and 5 bond coupling, the more extended coupling. But our instruments are sensitive enough to pick those up. So we're going to ignore them at the level of analysis we're doing for this class, but there is information in there. So just being kind of aware of that. All right, so let's keep going with this. And I want to look at what happens. So let's look at this molecule here. And this is similar to what the molecule when we first talked about nearest neighbors. So we've got this proton we're going to look at right here, the red proton. And it has 1 hydrogen, HA on the left, and there's 1 hydrogen on the right, HB. And up till now, we said, okay, it has 2 nearest neighbors, it's going to appear as a triplet. But if you think about it, HA and HB aren't really equivalent, right? HB is attached to a carbon with 2 fluorines, whereas HA is attached to this carbon double bond. So they are fairly different protons. So they might split us a little differently. So we're going to look at 2 examples here. We're going to say, what if the splitting is the same between those 2 protons? And then what if it's different? And I'm going to completely exaggerate the splitting difference here. But we're going to say, all right, I'm going to take proton A. And then the splitting due to proton, I'm going to look at my red proton. And the splitting due to proton A is 6 Hertz. So I'm going to say, okay, I'm going to take this signal and I'm going to split it. This distance here is 6 Hertz. Okay, so my y-axis or my x-axis essentially is Hertz. All right, so proton A split the singlet of the red proton into 2 peaks. But then proton B is going to split it, and it's also going to split it by 6 Hertz. So I'm saying that that's also 6 Hertz here. Okay, and so this is supposed to be to scale, and my scale's not that great here today, but I'm going to end up with a ratio of 1 to 2 to 1. I'm going to get 3 signals here. So this is going to be a triplet. Okay. So if the protons on both sides split it the same, I get the triplet that I would predict. And my intensity is 1 to 2 to 1, like I would expect. And we do that. Now, what happens though, if my coupling constants are very different. Let's look at that. So let's take our proton, which on its own would be a singlet. And now I'm going to do 12 hertz and 6 hertz. So my green proton is going to split it by 12 hertz. Okay, that's kind of a ridiculous splitting, but 12 hertz. And then my blue is still only going to split 6 hertz. Okay. So what do I get in this case? Well, I get a 1 to 1 to 1 to 1. And so what I would see here is I would see a doublet of doublets. Okay. So depending upon the splitting, whether these neighbors that are near each other have the same splitting or different splitting, I'm either going to see a triplet or I'm going to see a doublet of doublets. And sometimes we talk about resolving the triplet into a doublet of doublets. If we could split it enough so we could see the difference between those two protons, we'd get that doublet of doublets. And so, two doublets there. And so that's why we see that difference sometimes. Now I have a slightly more complex example for you here in this slide where we've got a quartet. So looking at those yellow protons that are in the middle of the slide, the difference in splitting is usually much smaller. Here it's 6 hertz versus 7 hertz, not 6 versus 12. That was a little ridiculous, but it made my point. So the signal gets split by 6 hertz, so there's a gap there. That was HB that was doing that. And then HA comes through and it splits every one of those signals by 7 hertz. So they're near each other, but they're not perfect. So it's what we get here is a 1 to 4 to 6 to 4 to 1 ratio, which is, oh, hey, it's Pascal's triangle. Pascal's triangle actually means something in real life. It's not just math. Don't tell the math profs I said that. But it tells you the relative heights of the peaks. So if they appear together, we can actually see two different things here. If we just get a pentet, if we just get 5 signals, the ratio is going to be 1 to 4 to 6 to 4 to 1. But we might get it to resolve into a doublet of quartets. So 2 quartets that are kind of on top of each other. Okay. So depending upon how different your coupling constants are, sometimes nearest neighbors on either side will split into different signals. Sometimes they'll appear as just being equivalent to each other. Can you predict which one's going to happen? Probably not. So you just need to kind of keep it in your mind. Okay, I see a lot of signals here. I know that it could be one of 2 options that are happening here if I've got protons on both sides. Okay. All right, last thing for today is going back to what I talked about earlier with the cyclopentadiene and maleic acid, which is these geminal effects. And I want to use it to transition into today's experiment with the Diels Alder. So the vicinal relationship is what we've been talking about up till now. Now we're talking about this geminal relationship here. Remember, Gemini is twins because they're on the same carbon. So that's why we get the geminal name here. And so we're talking about protons being separated. Now, a lot of times those are going to be chemically equivalent to each other. And we just treat them together. But there are times because of 3-dimensional arrangement where they're not. And that's what we're talking about here. Now, I put this slide in here so you can spend a little time thinking about it if you want how it happens. It's the same thing as the coupling constants before. The point being that the spin of one proton affects the nucleus that they're both attached to, which then can affect the spin of the other proton. So you end up with a low energy state and a high energy state. So if you want to kind of know a little bit of the theory, that's where it is. But here's what we're talking about, going back to our compound from before, talking about this proton versus this proton. Here was our double bond, right? So we've got electron density above and below the internuclear axis there. And so this is interacting with that. The other side is not. Okay, so if the 3-dimensional arrangement makes your 2 geminal hydrogens be different, then they're probably going to appear as different peaks. If they're in the same 3-dimensional arrangement, then they'll appear just as a single peak. Okay. Now, geminal coupling is a fairly small coupling. It is affected by angle. This is kind of interesting. If you look at the 3 angles that we've got here, 109 degrees, 118 versus 120 degrees, the amount of geminal coupling, 12 to 18, 4.3, or 0 to 3 hertz. So remember I said coupling can give you information about angles, and that's kind of nice. But what are we talking about here? On our really nice 600 megahertz NMR, a 6 hertz coupling constant is only 0.01 part per million. That's a little tiny number. But we can get the resolution if we're good, and we tune our instrument well, and we set up our experiment well. But it's a fairly small change that we're seeing there. Okay. And then I also said it's with angle. Here are just some more looking at the coupling constants, just wanting to show you that if they're on a ring, you can actually see that because it affects the angle of the hydrogens. So as the ring size decreases, the coupling constant becomes smaller, or you can say as the ring size gets bigger, your coupling constant gets bigger. So this is what I kind of want you to take away from this is I'm not going to ask you to make predictions based on these. I want you to know this effect is happening, and I want you to understand that we can extract a lot of information from the NMR, a lot more than we've done, and you will build on that in classes to come in the future. But as this was the place we introduced NMR, I want you to know some of the things that are happening and to explain why you see the 2 peaks in this week's NMR. Okay. So I already alluded to this already, but I wanted to put it in kind of textbook answer format here so you have it to study for. When are geminal protons going to be split and when are they not? So if the protons or interests are not free to exchange, and one is in above a double bond system and the other isn't, the resonant frequencies will be shifted. And we most often see this in bicyclic systems. So if they can't exchange, and they're in different electronic environments because of the 3-dimensional molecule, then they're going to split. Okay, here are just a few examples. This one is negative 0.42 versus 1.42, or 0.77 versus 2.99, or 0.98 versus 1.45 if you can get it on the bottom versus the top. So you can see they're definitely showing up different. These pi systems really do affect our bonding here. Okay, all right, we are almost here. Let's look at this week's NMR. I want to try to help you a little bit. So we're going to make this product. Now, normally I would have you talk to your neighbor, but and a few of you I can tell have people walking through in the background, but they probably aren't going to know what you're talking about. So in the chat, let's just do this. In the chat, how many different types of NMR signals would you expect in the proton? So Proton Nmr, I can't, NMR, how many numbers of signals? And I will tell you that because of using different instruments, you might get different answers, so you're not going to be wrong. So you don't have to worry about that. So looking at this molecule, and I'm going to help you a little bit. Let's figure out where all we have hydrogens, right? We have hydrogens here. We've got those hydrogens up there. We have hydrogens here. All right, no hydrogens on the nitrogen, none there, none there. All right, we're going to have hydrogen here, here, here. Wow, it's Friday. Here and here. Okay, so just as a ballpark, how many signals do you think you're going to get? Seven, 8, 9, 7, 8, 9, 7. And there are 33 of you here, so. Okay. Looks like we have somewhere 7, 8, 8 or 9. And I have to tell you, I'm not 100% sure. And let me show you why. I think that these two are probably going to appear as a single group because everything's symmetric on the other side of the molecule. I also, as a result, think that these two are going to be a single group. And then, however, I've got one of these over a double bond and one not. So that gets me 4 signals right there. Now down here on the aromatic, I'm really not sure. I could see this aromatic giving me 1, 2, or 3 groups. I could see all 5 of these appearing equivalent. Or maybe we're going to get these 2 and these 3. Or maybe we're going to get full resolution. We'll get these 2, and that 1. So if we did that, 1, 2, 3, 4, 5, 6, 7, I think we're going to get at least 7 signals. So let's see what we do get. Let's actually run it there. All right, so here is the chemdraw prediction of this. Okay, what happened here? So we definitely have these 2 are equivalent here at 5.6. That's those. And then these, the bridgehead ones at 4.38. That's those. Oh, it does so that these 2 are separate. Okay, 2.21. I'm running out of room here. They have to cross 2.46. I should have flipped this molecule. And then they say that we're probably going to get 2 different aromatic peaks. Now there's a little difference in the number there, but 7.57 to 7.58 we probably wouldn't be able to see. So 1, 2, 3, 4, 5, 6 peaks is what chemdraw predicts. Now again, this is theory, and remember chemdraw is just averaging over all molecules, so we're not sure. But I think that one of the things I do want to highlight, a lot of you came up with a number a little bit higher than that. So let's talk about why it's not necessarily higher than that. And I expected you to do that. I kind of led you to that with all our conversation about things being asymmetric. But both sides of this molecule are the same. These are all the same. And so that means that these 2 are going to be in the same environment, because the other side of the molecule that might have affected them is symmetric, similar to these 2 hydrogens right there. So those actually group together. I think several of you probably split them. All right, so let's look at what can we actually do. Whoops, I already wrote on that one. Okay, so let's zoom in on these geminal ones here, right? This here. Now that looks kind of like a mess. Wow, that is a mess. So let's think about this hydrogen right here. This hydrogen right here is going to be split by the green one. And as a nearest neighbor, it also has those 2 blue hydrogens there. So I could see it appearing as just having, if there's coupling constants are the same, I would expect it to have 3 nearest neighbors, which would give me a quartet. But it could be that they split, so I could get a doublet of triplets. I could actually just get a doublet, or I could even get a triplet. What did chemdraw predict? Well, chemdraw predicted a mess. I've actually heard this referred to, it's a multiplet, because we don't know what it is, or I've even heard it referred to as a mesoplet, which is just a mess going on there. So what can we actually get? Chemdraw kind of failed on us here. So the literature published spectrum of this molecule was here. So zooming in, we get a doublet of doublets, but it's not quite, you'll notice that there's little shoulders on these. Okay, they're really hard to see. But we ran this reaction with our NMR, because our NMR is obviously better than anybody else's. Okay, it isn't, but there are more powerful magnets. But when we did this in the fall of 2018, we actually split it into a doublet of triplets. So this is what we should actually see when we do this. And where does that come from, right? Well, that's saying that the green splits it into a doublet, and then the 2 protons that are in blue each split those into triplets, because there's 2 nearest neighbors, and remember it's n+1. So we actually get a doublet of triplets. We're getting full resolution of the geminal hydrogen splitting with our instrument. Cool, go us. So we can actually see that. So we can see the difference in that splitting there. Okay. So what I'm saying, just to tie it into the picture that we had before, here's our proton. I'm saying we split this into a doublet. Wait, actually, let me do it in the right color. So I'm saying that the green proton here split it into a doublet. And then I'm saying that the blue proton split into triplets. So I'm getting a doublet of triplets. Okay. And that's my last slide. So And it should be a Halloween poem. Sorry, I missed one. So that's the presentation. So what did we talk about? We talked about some basics in Diels-Alder. The experiment itself is going to walk you through more about the Diels-Alder reaction, talking a little bit more about the stereochemistry of the diene. Okay, that comes up in there. And then this week we're going to do this hetero-Diels-Alder reaction. Why is it a hetero-Diels-Alder reaction? It's a hetero-Diels-Alder reaction because it's got these nitrogens in here. It's not all carbons. We're going to be reacting. Our double bond, our dienophile, is actually going to be a nitrogen-nitrogen double bond instead of being a carbon-carbon double bond, which I always kind of like because it's nice, bright pink. It's this beautiful magenta pink color. It's kind of like if you took your phenolphthalein endpoint way too far and on steroids. It's this really pretty color. But it is the hetero-Diels-Alder reaction that we're going to do. We're going to make that product. And then we'll try to interpret the NMR on that one. Okay, so I'm going to go ahead and stop the recording here because that's the end of my regularly scheduled presentation.